So as of now, we've gone through error estimations, like different types of errors that we come across. Absolute error, relative error, and percentage error, and how to calculate them. Up to that part we have seen, and exact errors in rounding off process and truncation process, that we have to see, and how to do rounding off operation in Fortran and truncation operation. Okay, so that part we have to see, and apart from that, we'll go into the next session, solution of transcendental and polynomial equations. So this is a starting point where numerical methods play their role. Like let's say so polynomial equations are clear. Anything can be expressed as a power series of polynomial, any function. I mean, whatever function that we can express as a power series can be solved numerically. So that is a fundamental rule here. So if you cannot express the given function as a power series, you cannot solve it. Okay, power series means either a Taylor series or Leibniz series or any kind of series is a primary requirement for numerical analysis. Okay, so what is the Taylor series expansion? F of x is equal to f of x0 plus f dash of x0 x minus x0 by 1 factorial plus f double dash of x0 x minus x0 whole square by 2 factorial. So this is the Taylor series expansion of a function f of x. Okay. So here I am taking an approximation. I am considering the function. I am neglecting the higher order terms. So this can be written as f of x is equal to f of x0 plus f dash of x0 into x minus x. So whatever function you are given, solution of the function is what? What do you mean by solution? Let's say I have given a function f of x, some graph. So what do you mean by solution of that function? The solution means you have to write f of x is equal to 0. Means you have to identify the location of x. You have to identify the location of x where the function becomes 0. So you have to identify the location where the function becomes 0 and identify the value of x. So x is the solution. Let's say we call it as x naught. X naught is the solution. So it is the value of x where the function becomes 0 is the solution. So now I am assuming x is the solution. So then what happens? f of x is 0. So what happens to that equation? F of x0 plus f dash of x0 into x minus x0 is equal to 0. So here x0 is a point I am considering. x0 is under user control and x is unknown. Okay. Okay, here x0 is under user control. That may be any number. So we are expanding that function by considering the derivatives at a particular location. So Taylor series is obtained by evaluating the derivatives of the function at a particular point. So that point may be a solution or may not be a solution. So the Taylor series is conducted around a point. So that point is not necessarily a solution. Okay, so I am considering some point and I am taking an approximation for the Taylor series around that point. So now I am assuming f of x, x is a solution, so this becomes 0. I need to get the value of x, so which is unknown to me. I need to get that value. So if you write x is equal to what? What is x? So it is obtained by f of x0 by f dash of x0 okay, we'll simplify it. So f dash of x0 into x minus x0 is equal to minus f of x0. Right? So x minus x0 is equal to minus f of x0 by f dash of x0. In other words, x is equal to x0 minus f of x0 by f dash of x0. This is the approximate estimation for the solution. x0 minus f of x0 by f dash x0. This is the approximate estimation for the solution. Why? Why is it called approximate estimation? Why is it called approximate? Because we are neglecting all higher order terms. So if you consider all higher order terms, then it may be an exact solution. Since we are neglecting all higher order, second order onwards, we are neglecting all the higher order derivatives. So this is an approximate estimation for the exact solution. So we may get some other number. So we substitute it back into the function and check whether it becomes 0 or not. So the process continues till we get f of x is equal to 0. Okay, so this method is called a Newton-Raphson's method. Newton-Raphson method. The only condition for this method is the function must be derivable. I mean, the first derivative must exist for that function. If first derivative does not exist, or if it becomes 0, we cannot apply this method. So condition is the first derivative must exist. This is the only condition to apply this method. So now we consider some function. Let's say I am multiplying x minus 2 and x minus 5. I'm considering that function. So 2 and 5 are the exact solutions for it. Okay, so the function is x square minus 7x plus 10 is equal to 0. So I have to solve that function and get a solution for that. Okay, so I'm starting with program Newton Raphson. So I have to start from 7th column onwards. Program Newton Raphson. The first thing that we have to use is implicit none. And variables that I need are x and f of x. These are my two variables. So I'm defining my function. Okay, I'll define the function later. So that is my function f. F is equal to x square minus 7x plus 10. Okay, so what should I do? I have to take an initial guess. Enter an initial guess for x. And I'm reading that. So while absolute f of x so we have to consider absolute value of f of x, because the solution may be on left side or right side. It may be positive or negative, whatever result we are obtaining. So we have to consider absolute f of x. If it is greater than whatever accuracy we require, so what shall I do? I have to calculate, okay, f and f1 is also needed, right? x is equal to x minus f of x by f1 of x. So my new value of x is whatever value of x you are reading minus f of x by f dash x. So maybe you have to use do while probably. If while doesn't work, do while. So once the condition fulfills, then what? Then I have to define those functions. What is the derivative? 2x minus 7. End function. So if you want to add iterations also, what are the intermediate iterative solutions? Define another variable integer I, and here I is equal to 0. Always start with 1. Iteration comma I solution comma x, and rise the value by 1. I is equal to I plus 1. Iteration comma I solution comma x. I is equal to I plus 1. I starts with 1. So Fortran is not case sensitive. Even if you write small letter or capital letter, result does not change. This Newton-Raphson method has faster convergence compared to other methods like bisection method, fixed point method. So we'll see that in the next session. So this runs faster, and the error is of the order of second order, because we are considering only up to first order derivative. So error is in the second order. Rate of converging is also quadratic convergence. So that derivation part we will see in the next session. So this has quadratic convergence, whereas other methods are linear convergence. So they take longer time compared to this. Right? So the other methods we will see in the next session.